see pretty much the same thing I gave at the Monument meeting. The Monument Amateur Radio Club asked for me to present what we did for our Artemis 2. Let me get my thoughts sorted here. For our Artemis 2 effort. And so I came up with a slide set. I've made it a bit more generic. It was kind of specifically for that club. And so hopefully this one will go off a little bit better. But so what I'm going to cover here is, let's see, let's take care of some housekeeping. So if everyone could turn off their audio and turn off their video, it just makes things a little bit more snappy rather than having everyone sitting there eating your dinner in front of everyone. And so Deep Space Exploration Society's collaboration with NASA for one-way Doppler measurement tracking is basically our journey working with NASA. And we had quite an adventure and quite a few experiences collaborating with NASA. And to give you an idea of what we were doing, I'll talk about me first, sorry. Pretty much everyone's seen this slide before. Let's see if I turn on my laser pointer. Probably the most important point is this last one. This is kind of how I got involved with DSES, is that I consider myself a maker. Though I'm trained as a software engineer, a professional software engineer, I love working with my hands, and I've gotten an opportunity to build a lot of stuff for DSES. And that's kind of why I'm so involved in the organization. And for those of you that may not know what I look like, that's me next to our Venus-Earth, approximately 2K amplifier, 2K capable, 23 centimeter amplifier. And I'm here at the hub, just a little bit behind the focal point of the dish. So let's recap what Artemis was. Recap is that Artemis was it was a 10-day mission. It was initially launched. It came around. They boosted it up to a very high apogee, and they did a number of experiments with maneuvering, and then they came back around and they did their translunar ejection burn. Came out, went around the moon, and came back directly and splashed down. Now, though this artwork may have these nice loopy lines to it, if you really look at the trajectory of Artemis, it's about as complex as throwing a rock up in the air. You know, literally, Artemis went straight out from the Earth. At its furthest point, the moon kind of ducked between Artemis and Earth, and then it fell straight back down to Earth. If you know, depending on the frame of reference that you take, it was just a straight back down trajectory, with the moon giving just enough tug to turn Artemis around and bring it back toward Earth. So what we were trying to do is, if you notice that there was the term one way in the title, is we were collecting Doppler shift information from Orion's capsule transmissions. All the data that was coming down was encrypted, so we couldn't read any data or anything. But we were able to look at the carrier and figure out what the Doppler shift was. So this is where it all started. NASA had an RFI, a request for information, that they put out in August, and we returned our proposal, or our information, I guess, back in just like I think it was the day before the cutoff. October 26th is when we submitted it. For those of you that might be familiar with RFP, request for proposal, versus RFI, the only difference I can figure out between the two of them is you don't get paid for an RFI. So this was just a total voluntary effort. And so we replied to the RFI. Rick was the one that did a bunch of research and talked to a bunch of people to include just what he needed to include in the RFI to make us look desirable to NASA, and it succeeded. We were one of 35 sites worldwide that were accepted to participate in this experiment. And so that was this is our response in October. And by the way, all of this information is available on the DSES website. If you drop down projects, you can click on Artemis 2, and a lot of this, the actual response to the RFI and all that is on that website. Some of you might be wondering, why is NASA interested in private monitoring of its spacecraft? Why does NASA want Doppler information? Especially when you've got, huge dishes like this out there. This is the NASA's 70-meter, 230-foot antenna that's out in Goldstone, California. NASA is always looking for perhaps shifting some of their work to private industry instead of doing it themselves. So they were kind of experimenting with, what can sites around the world do for us? Are they reliable enough to be able to perhaps support this information instead of us supporting our own dishes? And also as a backup, if they were to have a problem with one of their dishes or something, could they possibly lean on private industry to fill in the gaps? So they were also looking at it for the possibility of backup. Well, what's really interesting is that the RFI went out in August. We replied in October, but in the intervening month, September, this happened. So that dish that I just showed you, DSS 14, was over-rotated. A lot of cabling was torn or damaged. Fire suppression systems ruptured and flooded the antenna, and it was quite a mess. What exactly or after this problem? I mean, the dishes operated remotely, so they really didn't know anything was going wrong until things started at their end. They started seeing failures in communication with the dish, etc. All of this is kind of detailed in a great report that you can read. If you just kind of Google, NASA antenna final report or something like that, it almost immediately point you right to this PDF document, and it actually is a pretty good document that will tell you everything you need to know about what happened. Well, almost everything you need to know. Actually, I threw this in here. This is one of the redacted pages. The majority of the document is unredacted, and is a very good document for writing that up. I'm going to do a little editorializing here a bit. So, reading the document, what it appears is that it's a very good report, except I think the conclusion kind of misses the mark, where they kind of blame the wrong people. So what it looked to me like is that this dish was severely underfunded, undermaintained. The people who were working directly on the dish were just scrambling all the time to keep this dish operational. And so in terms of it staying operational, these people were heroes, the way that they were working to keep this dish operating. But because the direct contributors don't get to write the report, but the managers do, what the managers did is they turned the word hero into a dirty word. And so these people that were scrambling to keep this dish running were thrown under the bus by management, and they blamed it all on the folks that actually kept the thing running. So anyway, I just wanted to throw an editorial aside there about this dish. That report does make some interesting reading. If you're at least bit interested in it, I recommend you go Google it and read it yourself. So let's pull this back to DSES and our journey with NASA to monitoring Artemis. Well, one of the first things that we did is that DSES is a STEM organization. So with the help of Megan Herron, who's a DSES member, who kind of trades her time between EADS, where she grew up, in Denver. She actually arranged for us out in EADS. So EADS, you can see, is way out on eastern Colorado, which is why DSES kind of considers itself, hopefully a STEM resource for far eastern Colorado, because there's not that much else out there. But in order to do some STEM outreach, Megan actually acquired the EADS Theater, and so in October we actually did a presentation. This is Paul Sabone speaking at the EADS Theater. And we actually had a pretty good turnout from quite far away as well. And our main speaker was Mark Pruill, who is the Orion Program Principal Network Architect for the Orion capsule. And so he gave probably about an hour and a half presentation on Orion and what it's trying to do and all that to the theater. After that, we kind of turned ourselves to our site and what we needed to do, because following spacecraft was an entirely new mission for DSES. Required a little bit more accuracy. And again, I would suggest, could everyone turn off their video just for better response? And also it's covering up my notes. So if you could turn off your video, I'd appreciate it. Okay, let me rearrange some things then, if I can't. That's out of the way. Okay. So we're looking at a little bit more accuracy than our astronomical observations. So we have a lot of prep work to do to get ready for the Artemis 2 effort, with a possible launch in February. And one of our lingering questions is our antenna is almost 70 years old. Is it still correctly calibrated or columnated? So one of the first things we did is we did an experiment where, actually two experiments. One involved pasting ping pong balls in regular intervals all over our dish and taking basically stereo pictures of the dish so we could figure out its curve, as well as mirrors. If you look very closely at the bottom here, you'll see some mirrors that are pasted, as well as alternating with ping pong balls. So we did this, and one of the things we did was from quite a distance shine a light onto the dish, and sure enough, everything focused right at the focal point where we expected it to. In the dish here, you see Emil Weiskel, Pat McDivitt, Alex Nersasian, and I'm taking the picture. Always interesting getting into the dish. It's not OSHA approved, but we can get up in there. Another thing we did is we wanted to see how accurate the dish was pointing. So here we are about 8.5 miles away from the dish. So the dish, if you look very carefully, is right here. And of course, Haswell and its grain tower is off here in the distance at about 13.5 miles away. And at this distance, a 1 degree error is about 800 feet off from the location. So we were doing this with 8 gigahertz. We have an 8 gigahertz beacon here, and we were waggling the antenna around here to see this was positioned absolutely perfectly due south from our location. And sure enough, when the antenna was saying that it was south, it turned out to be directly due south. So with the dish columnation kind of verified, we moved on to the feed. So we used just an off-the-shelf amateur radio feed by RF Ham Design, though we did tune it for the S-band frequencies that the Orion capsule was transmitting at. But except for that, this was a box stock feed that we used. And attached to that we had, so the signal coming down from the Orion capsule was circularly polarized. And let's just leave it as saying that there was a lively discussion on whether we were going to see it as right-hand circular polarization or left-hand circular polarization. And it got me to the point where I realized that if you ask 4 RF engineers, good RF engineers, over a period of time, their opinion on something, you're going to get 8 different answers. So we had a hard time settling on this. So the solution was we actually put in a low loss relay, latching relay here between the 2 polarizations that fed into our first preamp. So this way we could actually switch on the fly between right and left to figure out which one was the correct one. From the feed, we then went into a bandpass filter and then a splitter. So our plan was that we would actually have 2 receivers running in parallel. One of the receivers would be in our operating center down in the building. So we had to lift that with, well, we initially started with 2 more preamps after the splitter, but we ended up dropping the second preamp after a while because we were overloading the front end of the SDR down in the control room. The second connection actually went to an SDR that was in the hub behind it. So we'd split the signal, we'd amplify the signal and send it down to the control room, or we'd just send the signal directly to the SDR, which was like 1 foot away in the hub. So once mounted, this is our high-tech weatherproofing that we put on the feed. But you can see this is the left-hand circular polarization side. And the preamp is actually now vertical and like a horizontal in the previous picture. But it then fed inside to our equipment inside the hub. So here you see that RF chain again of the bandpass filter, splitter. This number 2 went right to the SDR here. And this one, these 2, well, again, it was eventually just be 1 preamp, would actually send the signal down to the control room. And there's a Raspberry Pi up here for collecting information and a number of pieces of support equipment. This is inside the hub, which is behind the focal point. If you look up here, you can see the back of those plastic baggies that are giving weatherproofing to our feed. So while we were working on the feed, we were also updating some of the equipment in our control room. So this is our control room, and kind of from left to right, we've got dish positioning control here. We've got kind of our RF area here, where the RF comes down from the feed. We got a number of computers here. We've got some test equipment here, and over here is our time base. So, and I will talk about each one of these a little bit individually here. Going first to the left side. So this is our computer control for moving the dish and keeping the dish on an object. There's both computer control, and up at the top here we have a manual dish control. You can see right here. I want you to keep that in mind because this manual dish control is going to come up again. Over here we actually have two LMR 600 that goes up to the dish. They terminate at these 2 locations, and then we have a cable running to our SDR, which is kind of unceremoniously thrown on top of the cabinet here. We've got a power supply for the preamps, for running the preamps, and we also have this is a little Raspberry Pi that reads out where the dish is pointing. So we have kind of our dish positional control here and our kind of RF area here. Then on the I guess we're going to go right to. So this is kind of what the computer control looks like, where you give it an object, you can kind of see Artemis in here. So again, we were faced with kind of a new tracking requirements. Up to now, we've been tracking celestial objects, which in the simplest are very distant objects, such as neutral hydrogen or pulsars or something that that are very, very distant. So they're basically just sidereal time that we have to clock on. But man-made objects that are orbiting or have a trajectory, we had no way of doing that. And this system is called System 1. You can see it up here, System 1. And it was written by Glenn Davis, Louis Putman, and Phil Gage. And again, it was built for tracking celestial objects, but now we had to do spacecraft. And so they came up with a very ingenious idea. There's a page from JPL, which is called the Horizon System. And the Horizon System has ephemeris information for not only solar objects, like planets and moons and all that, but also for man-made objects. And so using the Horizon System, you can actually query the system and find the azimuth and the elevation of where you need to point the telescope in order to be on the object. To give you an example here, I ran an output for the Mars Reconnaissance Orbiter. You can see up here, Mars Reconnaissance Orbiter spacecraft. And just to kind of do an output, I did it for every couple hours. This is information from a week ago. I couldn't really do this with Artemis because Artemis is no longer up in space, so there's no information for it. But for any object in space, or any solar object, basically you can use this JPL page to find out exactly where it is. For example, if you have optical telescopes and you want to catch, you might be able to catch a satellite or something like that. If you knew where to look, you can use this JPL page to find out the actual azimuth and elevation at a certain time and point your telescope there if you wanted to see it optically. So what would happen is that you tell it to track on Artemis, and the whole dish slews over toward Artemis until Artemis is inside of, this is a 3 dB down circle. So as long as Artemis is kept within this circle, we know that we will be less than 3 decibels down from a full signal strength. And so this is basically the way that the computer system works. If we go over to the other side of the desk, we have some test equipment here. We got a frequency generator and there's an oscilloscope down here. But this is the interesting part. So this is a rubidium clock that was donated by Art Seppin. Actually, it's a refurbished and probably better than it was when it was new, rubidium standard. And it inputs into an interval timer. And then for those who know Rich Hambley, this is something his company produces. This is a clock system. And then we distribute the clock signals using a Stanford Research FS735 distribution amplifier. By the way, for those that are really interested, this is an HP 5065A rubidium standard. And this is an HP 53131A time interval counter here. And this is what gave us very, very accurate time information in order to report back with our Doppler information that we were collecting for NASA. So we now know the dish is okay. We have a way to receive the signals. We have a way to keep the dish on a man-made object in space, and we have a time standard. So we're basically ready to go. So let's go back to the Artemis mission here. So Artemis's first launch window was in February. And quite frankly, we are so glad they had a helium leak and rolled SLS back in, because we were not ready in February to do our job. We would have not been able to generate any information if it had gone off when it was first planned. But by March, we were ready. Along the way, somehow I became the organizer of the on-site staffing effort. The reason we have people on site is exactly for the reason of avoiding what NASA had NASA had with their DSS 14 antenna. We always require someone to be on site observing the antenna at all times to make sure that it doesn't run away. And it doesn't run away. It runs away very, very rarely. But we're going to come back to that. So all we knew, or because I kind of became the de facto leader, I was kind of like Hague, and it's like I said, I'm in charge here. And I looked at this first orbit. So the first 24 hours is this highly eccentric orbit that Artemis took, or the Orion capsule took. At its apogee, it was about 44,000 miles, so it's well outside of the geosynchronous satellite orbit, and its low point was about 115 miles, so less than that of the ISS. And because it was very hard to predict when it would be above and below the horizon before the launch, I decided that we just would not staff the antenna the first 24 hours. We would wait until the translunar ejection burn, which happened here, and we were on our way to the moon, and then we would staff the antenna. So, and again, our goal was to simply monitor the transmissions from Orion and determine its Doppler offset. So as it's traveling out from the moon, its signal is going to be shifted down in frequency because it's moving away from us. And as it's coming back from the moon, it's going to be shifted up in frequency because it's moving toward us. So on April 1st at 6:35 p.m., Artemis 2 launches. At that point, I had 24 hours to try to staff people. But the first thing I had to do was figure out, we had to wait until JPL had populated their page in order to know when was Orion going to be above the horizon for us. And it turned out that in the United States, it was very conveniently above the horizon for us from midnight to 9 a.m. So this made it a heavy lift to get people to staff the dish down at the Haswell site. Amazingly, our members came forward and populated all of the times that we needed, including, Larry Stewart here is on the call. He came all the way up from California to handle the last 2 days out here. But we did get complete staffing for everyone. And, the bad news is that basically you were up all night monitoring the dish, make sure everything was kind of going okay. And so what happened was, because the adventure continued here, I'll take the days one day at a time. So the first shift was Louis Putman and myself. And this was actually a good, I'm really glad that Louis went down, because Louis was one of the System 1 folks. So if we had any problems with the brand new software that was going to track Artemis, he was there to help out with it. So what I like to call the Midnight Oil Crew was myself and Louis. And the first thing we did is we encountered some focus problems. And this was kind of the culmination of a number of problems that happened, in that it turned out NASA had failed to tell us. They told us, we want you to record data from this time to this time. What they didn't tell us is, and oh, by the way, we won't be transmitting all the time. So we were expecting for a signal to be there, and we started monkeying around with the focus because we were seeing nothing. And then it was compounded by some misinterpretation of data, and we basically moved the feed itself well away from the focus point. And it's one of those things that in retrospect was something we should have realized, that we were doing something wrong. But at the time, in the heat of the moment, again, this hero mode, you're trying to get things working. And so we were kind of scrambling. But and so really over that first 9 minutes, we collected about 2 minutes of data. But what helped us eventually is there's another cool site called the Deep Space Network now. And DSN, could you hold on just a moment? Oh, okay, I'm back. So what we were able to do is we were actually able to see when Artemis was transmitting here. So this is NASA's 3 major sites worldwide: Madrid, Goldstone, and Canberra. There are a few satellites here that just off the top of my head I can recognize, like the Lunar Reconnaissance Orbiter and the Mars Reconnaissance Orbiter. And Juno is here. And this is a live site, so you can see who's transmitting, who's receiving. So like this, Juno, they're both transmitting and receiving information, or something like, I don't know what M010 is. Just a moment here. Something just popped up. Can someone tell me, can you still hear me and see me?
Yes, we see
Anyone?
you. We hear you and see you.
Okay. I don't know. All of a sudden I got this pop-up saying I've been signed out of a meeting. So I don't know where that came from. So this is I don't know if it's actually transmitting or receiving. The interesting one here is out in Madrid. Their big 70-meter telescope, when I did the screen capture, was actually receiving Voyager 1, which you can see over here. And a little trivia here is in November, Voyager 1 is going to achieve the distance of 1 light day away from Earth. So it's going to take 2 days for a round trip communication. Where they have DSN, that's typically it's being done for maintenance. Not surprisingly, here's DSS 14 that they damaged, and it's sitting here in a maintenance mode. But we were able to look at this, and when we finally figured out that Artemis was not always broadcasting, and so that helped us quite a bit from that point forward if we were trying to dial things in. So after collecting a couple minutes of information, Lewis and I left the site, and then Bill Miller came down to take over for the following day. So Bill Miller, Mario, Travis showed up, and Bill Miller quite wisely simply reset the feed to its predicted focal position physically, and all of a sudden there was data. So he had a very successful night of receiving data, and at this point our confidence was high that we can track the Orion capsule. And the 3 of them just kind of took it easy during the day. And with the news that we were getting data and all that, everyone started to relax. Then we get to the 5th day. So on the 5th day, there was a new member of the crew called Murphy. And so Bill gets up at about midnight, tells the computer to swing the antenna counterclockwise to Artemis, where Artemis 2 will soon rise. And he walks out with his coffee, looks up at the dish, and despite the computer saying it's going counterclockwise, the lights on the panel saying it's going counterclockwise, the dish is rotating clockwise. This is why we have people on site. And so Bill, this is eerily similar to the DSS 14 antenna failure that NASA had. So the dish is rotating the wrong way. So Bill stops the antenna immediately, wakes up Mario and Travis, and fires an email off to the board and the System 1 folks. And this is where we start getting lucky, because Glenn Davis, who wrote most of the ephemeris type software for the System 1 system, happens to be vacationing in Hawaii. He was out on Maui, which is 4 hours behind us. He's out there with his wife, and he immediately responds to Bill, and the 4 of them start trying to diagnose the problem. I'm pretty well convinced that Glenn's wife will never speak to us again after this experience. um, so they start debugging, and and the problem turns out to be specific to the computer control. I showed you that manual control panel. The manual control panel, the dish moved just fine with, but the computer control panel, when you send a counterclockwise signal to it, it would start turning clockwise. So Glenn kind of narrowed it down to a device within the system called LabJack, the LabJack general purpose I/O module, and it turns out he has a spare. Of course, he's in Hawaii, and his house is here in the Springs. So Lewis goes over and breaks into his house, and gets the spare part and heads down with it, and gets it installed. And unfortunately, this doesn't fix the problem. And at this point, I'm sure Glenn's wife is considering divorce, because Glenn is spending an awful lot of time with us on the phone. But I should mention this midnight crew. So Lewis was down there with Paul and Jeff, and trying to get things working. So at this point, we made a call. So on day 7, we canceled all the on-site activities while we tried to figure out, can we recover this? Is there any way to recover this problem? And we come up with a way that we believe we can run the antenna manually while letting the computer show us where to point. So we kick off the staffing again. And so our midnight crew for that was myself, Ann Haney, Richie Larry, and Larry Stewart, who again came out from Chicago. And so we have a plan, but will it work? So we switch the manual, we switch everything to a manual control, but we also fire up the computer and tell it to track Artemis 2. And it works flawlessly. And we gather a full shift's worth of data. Now, by working flawlessly, what was happening is this is again, this is kind of Artemis within that 3 dB circle. And for the first half of the night, what would happen is Artemis, because the computer wasn't tracking it automatically, it would drift off into this direction. And just as it would get to the circle, we'd have to reach up and toggle the azimuth and the elevation, and we would bring Artemis down to like this part of the circle. And then we would just let it drift across like that. And so basically all night for 15 to 30 every 15 to 30 seconds, we'd have to go up and run these switches. So we were doing the computer's job. And so for 9 hours, I'm glad we had 4 people there, because we could have 2 teams of 2, and one person would run it for a while, another person would run it for a while. And when that team burned out, then the next team would come in and just run it. And so we were able to get good data over the night by just letting it bounce back and forth between these two locations. Now, I mentioned there was a person there named Richie Larry, and Richie, let's see. So the next morning, Richie takes off because he has a luncheon with a couple friends back in Colorado Springs. And one of those friends is Tom Eggers. And Tom Eggers has had nothing to do with didn't even know DSES existed. And Richie gets there, and during his luncheon, he coins the term that what he did is all night he played the world's most boring video game. And despite that, he enjoyed the experience. But we've kind of adopted that as the description of what we had to do, is run these 2 toggle switches just to keep the thing within that circle. And Tom Eggers, I guess, was enough of a masochist that he actually called me and said, "Hey, can I come down and help?" So Tom Eggers actually joined our team on the last night, and again we ran it 9 hours. We ran it manually. Just lather, rinse, repeat, as I say here. We ran it manually all night to gather another full shift of data. And then about 9 a.m. or so, we were done. We closed down the site, and again because the capsule is now approaching Earth, it was going to get to the point where we weren't sure when we could receive data from it. So we decided not to collect data on the last day. So the next day was splashdown day for the Artemis 2 capsule. So what did we gather? I'll first show you the pretty pictures that our software would generate. So this is an example of the Orion carrier being received, and here there's a positive Doppler shift. By the way, we had an SDR in the control room in parallel working with an SDR in the hub. So this data is from the SDR in the control room, and here's some Doppler information with a best fit line drawn through it to measure the Doppler shift, and kind of a deviation with a smoothed line from all the data points that we were gathering for the Doppler shift. This is the equipment that was in the control room. For the equipment that was up in the hub, we had very similar software that was receiving it. So this is a negative Doppler shift. So this is probably on the way, or would have to be on the way out. And again, kind of the data it was collecting. But ultimately, all NASA really wanted was an accurate time and a frequency. They didn't want any of their, the 35 stations that were accepted for this study. They didn't want them to do the processing. They wanted to do the processing themselves. So ultimately, what we sent NASA was simply an ASCII file that would have the time and the frequency that we received. And these are there were several files, several very large files that were generated that were shipped off to NASA. As I mentioned at the very beginning here, this was the result of an RFI, request for information, rather than an RFP. And the difference being, again, that an RFI, you don't get paid for, but you do get a participation trophy. So NASA sent us this certificate about us participating in the Doppler shift, one-way Doppler shift experiment. And we have this now. We're going to have this proudly displayed down in our building in Haswell. So that's pretty much the journey that we took for Artemis 2. We are looking at Artemis 3. Now, Artemis 3's, for if anyone hasn't heard, Artemis 3 was going to be the landing on the moon, and it has been scaled back to basically a test flight with several rendezvous, all in low Earth orbit. So, Artemis 3 is going to go mid-2027 to early 2028. And we're looking at if NASA wants information from that, we can do that. Fortunately, what we can do, because this will be more of a satellite behavior rather than a lunar ejection trajectory, we can use just a simple azimuth elevation mount with a Yagi to track it, which means we can run this remotely without any people on site with like a simple Yaesu mount and a Yagi. So this one should be a lot easier to do because no one needs to travel down to the site in order for us to use the Yagi antenna. Again, that dish, we never run the dish without someone on site.
Roger?
So, yes.
I have a point of scientific interest here. Can you go back 6 slides?
2, 3, 5, 6. This one?
That one, the sinusoidal one. And one of the interesting things about this, I think what this is showing is I'm not entirely sure, but I think what this is showing is Earth rotation, right? So the
Rick
Doppler effect of the Earth from going into the satellite versus going away from the satellite.
The minutes seem too short.
Yeah, the minutes are too short, but I have no other explanation for that.
Well, the Earth's rotation is inconsequential to the velocity of the aircraft.
Well,
well, not inconsequential, but it does. Well, I don't know. Rick is on. Rick, can you explain this graph a little bit better?
Yeah, it's definitely not Earth rotation related. The residual is if you take the Doppler curve and normalize it, this is what you get left over. And this is just movement of the capsule, nothing more than that.
Okay. All right. Well, that clears that one up. Good.
Okay. And
Sorry.
your timing was perfect because this was the next slide. And before I take questions, I just want to go through the one or two slides here. These folks are heroes because these are the ones that showed up and stayed up all night from midnight to 9 a.m. That were allowed us to actually run this experiment by manning the or babysitting the telescope while we were down there. I have Glenn over here because he contributed. I don't know. It's a break even here because he contributed more because he was on vacation, but he contributed less because it was actually like 8 o'clock instead of midnight for him. So it's a break even, but we appreciate Glenn. We appreciate his wife for being so understanding on their Maui vacation for having us call. And then this. I'm actually looking to the board. I hope this is an inclusive list of everyone that contributed to. I'm just seeing it. Yep, Rick's there. I was worried that Rick wasn't there, but contributed to the effort of tracking Artemis. And now I'll take vacations. I'll just leave this slide up. So this has the DSES Science page. It has that JPL Horizons page and the DSN Now, which shows you what telescopes are receiving what satellites. So, any questions? Well, either I did a really good job or a really poor job.
I'd say really good, Roger. You didn't have too many people drop off.
I'll get out. I'll stop sharing here and we'll get out of that.
Nice.
So yeah, so that's what I presented. Bill, I will get this slideshow to you. You asked for a copy of it. You probably saw the differences between this and the one I did at W0TLM.
You bet. Yep. Look good.
So everyone has at this point, everyone has permission to turn on their video if they want to. I apologize for making you all turn it off.
Roger, I have a
yes.
Good job. Good presentation. Appreciate it. Question: what's the biggest lesson learned of everything you showed us?
Oh, you're going to ask me philosophical questions.
In your opinion, in your honest opinion, what would you take as the biggest lesson to learn?
Alex, I'm actually going to think about that one a bit. I think, generically a little bit more. Well, I would say more lead time, but we actually solved some of the problems that now, so we should be able to react more quickly to requirements. It went surprisingly well. We had our problems. Oh, I know, Alex. I'm going to table your question for a second because I know someone out there has to be thinking about what went wrong with the computer drive. And I didn't answer that question. So Glenn thought that it was the lab jack, general purpose IO card, and he was very, very close. there's a daughter card that plugs into the lab jack, which is a digital to analog converter card that has 2 DACs on it. And one of the DACs went bad. And talk about Murphy, because this system has been running for how many years, Bill? I mean,
Well, yeah, we've had that system in there for about 8 years.
and all of a sudden we have this, and we've had hiccups, but we haven't ever had a hard failure until then. So it was just, luck of the draw that we got nailed.
I think I had some thoughts. One of the thoughts was, we were kind of going down this path of doing a lot of things that NASA didn't even ask for. And NASA didn't give us a complete set of data. And if anything, getting contacts within NASA that could have answered some of those questions. One of the things about some of the other groups in that group of 35 different people that were going to do this, a lot of those sites are commercial sites, and they had done stuff with NASA before, and they'd also tracked Artemis 1. And so they had some experience from Artemis 1 that we did not have. So I think just getting contacts within NASA that we can really, nail down, what's really going to happen would be one of the big things, because that left a lot of questions and caused us to do a lot of work that we may not have needed to do.
Yeah, and NASA, I believe, has been working with the same people for so long that there's a large amount of tribal knowledge built up. And so things that they take for granted, they don't communicate. And us being, the new kids on the block, didn't realize, for example, that they're not, if they say, we want you to collect data from here to here, it would have been nice to know that we aren't transmitting that entire time, only, occasionally during that window, because we were expecting them to be transmitting all the time. And that caused us to go off the rails.
I'm curious to know who the old blocks are on the block, the old guys on the block. Is there a list of the 35 participants?
I guess more by old guys on the block. I mean, not necessarily the people.
Well, I'm interested in who our competition was.
It's listed on the NASA site.
Thank you.
Yeah. Hey, Roger, we went into this thing and we were the new kids and we definitely learned a lot. And I think this is the reason why we do these things to push ourselves, to stress ourselves to the point where we actually grow. And doing this, we've actually grown the capabilities of what we think we can do. And this is a great opportunity for us to learn. The other thing we took away from this experience was we need to have spares. Like we never thought we needed spares, but now we need to go through our architecture and look at items that may be susceptible to failure at some point, because most of those components that are up in the pedestal do not have any kind of they're not sealed in any way, or at least not too much. And the result of that is that things can go wrong. So we've learned what things can go wrong. I think that was one of them, and that's actually a positive, I think, Roger.
Well, I think we learn more than NASA learned from us what we sent to them.
That's a good point. Yeah, and that's the science of all this is the goal really wasn't so much to get the Doppler data. The goal was to see if we could even do it and what it took to do it and all the things that could go wrong and how we get around them. And so I think we accomplished the real goal, which was more of a scientific exercise than just sending data to NASA.
To us, this was an experiment.
Yeah.
Yeah, and the work that the System 1 folks produced by changing their their celestial tracking to actually, man-made object tracking was a huge, I don't want to say improvement, enhancement's the word I'm looking for, to their software.
And just look at the timing. I mean, the timing, the rubidium clock now is something that's part of our architecture, which we never had before. We were using GPS before, which is a toy compared to what we have now. So we're actually our capability in terms of tracking things in deep space has gone up exponentially.
Well, we didn't have 8.4 gig before this. So this was the catalyst that put us into 8.4 gig operation.
Well, this one was 2.2.
I guess this one was 2.2, but in the process, we did a lot of additional work and Alex did a lot of work on that, and so now we have the higher frequencies.
We're moving.
By the way, Alex pasted in the chat area the link to the NASA site that lists everyone that was part of this study.
Any other questions? God, you guys are so smart. Anyway, this is thank you, Roger, for doing this for us. We were recording it, I hope, and we're going to post it on the YouTube channel later this week. I'm going to get Bill Thomas to edit out the first parts and just have your presentation in there, Roger. So it'll be forever on the internet.
Oh, lovely.
You will be famous. 50 years from now, they'll go look back at you. Anyway, so given that, one last thing is Scott McIntosh, who was supposed to be here tonight, was he had a family issue that he had to take care of, and he was going to be out of town. So he did offer to come back, in a week or two or whatever we need. So I'm going to work with him in terms of timing, and I'll be sending out another notice for that science presentation, which is going to be on the sun. Okay.
I'd like to add that our next meeting is the engineering meeting, and we don't have a topic for that yet. I know that Glenn, the system, the System 1 folks are going down this week sometime. They may have something to report when they come back, but I'm always open for topics for the engineering meeting. So if anyone has anything or wants to hear about something, please get a hold of me or Paul.
That's for sure. Okay, guys, I'm going to turn off the Zoom now. But thanks again for participating. I think we had 28 people at one point, and we'll see you guys the next time we come on. And thanks for everybody for your time today.
Thank you.
You didn't want
Great
to call
presentation, Roger.
What's that?
They didn't want to.
That was a great presentation. Sorry we missed last week.
Well, it was pretty much the same thing. I just tuned it up a little bit. So you missed the rough one and got the not so rough one. I'm not going to say the smooth one.
That was great.
Yeah. We were in an RF dead zone, so we couldn't get on.
Okay.
If anybody has ideas on more science presentations, or who wants to give one, please contact me and we'll set it up.
Well, I'm hoping to be able to get some exposure down here. Right now, I'm working on a presentation to the superintendent of the school district in Dakota for ham radio, and seeing about either starting a club or maybe getting a class like Dara has done in Colorado Springs. So hoping to be able to kind of merge DSES in that as well.
That's great. Thanks a lot, Rick. Before I forget, everyone, mark your calendars. October 10th is our open house where we bring in everyone from outside to come in and enjoy some great food and hear their voices off the moon, because the moon will be up all day long, at least a good part of the day. Let's put it that way. And we'll be able to do some moon bounce there, either on 2.3 gigs or 1296. Well, one or the other, I guess, is probably what we'll have running by then.
You said
And,
the 10th?
We may be in Colorado then.
Yeah, that's October the 10th is a Saturday. And
I sure wish I lived closer.
well, you know, they have these things called airplanes, and there's some pretty good rates on right now. If you look at the Tri Frontier, they get some pretty good cheap rates. $38 round trip. That's what I'm doing to Houston and back.
I paid 19 last time.
Show off. You can get these crazy flights. And by the way, on the 9th, we're going to have a number of, there's a homeschool group in Southeast Colorado that will be visiting our site, and we're going to be giving them a presentation on space for their kids. So that's what we're going to be doing there. And if you want to come down and volunteer sometime, again, we're available to do that. You can come on down on the 9th and or on the 8th and be ready on the 9th, and then stick around for the open house on the 10th. So there's some opportunities for y'all.
Paul, do you want me to do financial quick report, or we're good?
I think maybe not right now. We're okay, but thanks for offering. We'll do that at the next meeting, okay?
Roger that.
Thanks, guys.
Thank you, Paul.
All right. Good night, all.
Have a good evening, everyone.